Good morning, everybody. Hopefully you're ready for another morning, sunny morning of organic chemistry with Dr. White. And today I'm talking about carboxylic acids. A couple things. One, don't forget for today's lab, you need a long sleeve top or coat, or lab coat. Be on time. I will enforce that if you're late more than a couple of minutes. And let's get going. Talking about carboxylic acids. How do you know you have a carboxylic acid? Carbonyl, carbon, double bond to oxygen, hydroxyl group, R group. We're talking about ways of making it, but before I do that, anybody happen to pick up a bottle of vinegar, look at it and say, oh, you've got acetic acid in it. That's a carboxylic acid. You do that. Think about it. Organic chemistry happens everywhere. All right. I talked about two ways of making carboxylic acids. This is another one, and this method is really cool. I mean, it's a really cool method. And the reaction is reaction of a Grignard reagent plus carbon dioxide. Second step, I just have H+, but really you can't go out and buy a bottle of H+. Usually it's a solution that usually for this class means water. And what you get is a carboxylic acid that's one carbon longer than the R group you started with. Again, the Grignard reagent allows you to do something very special, and that is create a carbon-carbon single bond. Now, let me go through this certain mechanism, so you understand what's happening. What I'll write underneath, you don't have to copy, but sometimes students wonder what is going on. Think of a Grignard like, and I use the quotes, like R minus MgM plus. And a carbon with negative charge is not happy. It's a nucleophile. It's looking for something with a positive charge. Now let's look at carbon dioxide. Carbon dioxide. Now if I use my magic organic chemistry hands and go like that, look familiar? A carbonyl. And therefore, what do Grignards do with carbonyls? Because carbonyls are slightly polarized. Says, ooh, positive charge, I'm going to tap that, open it up, and now this is the full charge. This carboxylate anion, this is the conjugate base of an acid, in other words, it's the base, so if I add an acid, it will be neutralized or go back to the acid, and that's what H+ and water does. And again, it's that special way of making a carbon-carbon single bond. So let's look at an example. And if I do the following reaction, if I mix these chemicals together in that order, what do you get? Well, look at what are you dealing with. What's different? Magnesium halide of Grignard. This is different carbon dioxide. Second step, acid and water. What do you get? A carboxylic acid that's one carbon longer than the R group. Here's my R group, 2 carbons. I can write that. And then my carbonyl comes from the CO2. I'll write that. And I know there's 4 bonds to carbon, so I can put it in the hydrogens. Now, why did I say earlier this is a real cool reaction? Because the way you can do it in the lab, and I've done it, is you make your Grignard, you get some dry ice. Is everybody familiar with dry ice? It's a solid at room temperature. It's carbon dioxide. It's really cool to play with, and it's really cold. And you just throw in some pieces of dry ice in here, let it react for a while, then carefully add some acid and water, and you're done. And it's really cool. By the way, I've worked also with dry ice for cooling baths, other reactions like this one I ran. And dry ice has a boiling, or actually it's not boiling, sublimation point. It goes from solid to gas at minus 78 Celsius. And I work with isopropyl alcohol baths with dry ice where you're running a reaction at minus 78. I do a lot of that. But this is fun to do, and you make a Grignard. Use a Grignard to make carboxylic acid. CO2 is bonded to the carbon with the Grignard. And why don't you try this one? As you can tell, I got my acid shirts on. All right, let's take a look at this. Question is, what is the product or products from this reaction? And you have to identify what functional groups you're dealing with, which is, I say, what's different. Ooh, magnesium chloride, Grignard. Remember, X can be chlorine, bromine, or iodine. And you know how to make Grignard reagents. And I have carbon dioxide. Second step, acid and water, or acid and some solvent. And what happens, you get carboxylic acid, one carbon longer than the original R group you started with. What's the R group? Isopropyl. Therefore, my R group, my carbonyl, and hydroxyl group, and that's the carboxylic acid you get. You can see it now. Now can you see it? And that's how you do it. And these are very high yield, efficient, nice, fun reactions to do. Anything with a Grignard reagent is fun, but then again, I'm quite biased toward it. On test number 3, like test number 2, I have 3 or maybe on this one even 4 synthesis problems. Any more would be cruel and unusual punishment, which so far is still outlawed by the Supreme Court of the United States. And I'll do this one, then I'll let you have fun and do one too. And the question is, what's the starting material for this following reaction? Another way of putting it is, how do you make this product with this reaction? Well, you come over here and say, what's different? I've got a ring that has carbons and hydrogens. Ooh, carbonyl hydroxyl group, carboxylic acid. And what do I react with carbon dioxide to give a carboxylic acid? I better warn you, after March 20th, my hydrogens go downhill when I draw them on the board. Actually, before today, I went downhill. All right, so what do you start with? A Grignard. Since I didn't give you any kind of salt formation, what is X? Whatever you want it to be. Well, what's our cyclohexane ring? Therefore, what's my question mark? This Grignard. And let's see, I'm in the mood for bromine. I could have put chlorine, I could have put iodine. Any one of those would be correct. And that's how you do synthesis, which is the really fun part of organic chemistry. But now I'm totally biased in letting you know that. This is why I became a synthetic organic chemist. And why don't you try this one? Let's start.
On the exam, will you have the CO2? Okay, so it will never be two blanks for this type of
It
problem?
will be just like this.
Okay.
Secret, if you notice my problem sets and problems I do under board class are similar to it. If this were a senior level or a graduate level chemistry, organic chemistry, then the answer would be no. But this is not, and therefore, that's how I would write it on the exam. Oh, I gave away a secret. Actually, if this were a graduate level course or even 2 semesters, I don't know, 2 semesters, a question like this would read, with alcohols of 4 carbons or less, how would you make that product and not do anything else? Actually, I had a test like that. All right, let's do this. What's different? What functional group are we dealing with? Carbonyl, hydroxyl carbons, carboxylic acid. We're reacting something with CO2, second step acid and water. What do we use to, what do we react with this and then this to make that? And that is Grignard. What's my R group? What's attached to the carbonyl carbon? Carbonyl, carbon double bond to oxygen. That, how many carbons? 3. Again, this is part of the semester, you have to know how to count up to 10. 1, 2, 3. Which carbon is attached to my carbonyl carbon? The end one. And what do I have? A Grignard. Let's see, I have to use iodine for a while. You can also put bromine or chlorine, because X here can be chlorine, bromine, or iodine. And that would be how you do it. And that's how you make carboxylic acids. And don't forget, the next time you have ketchup or mustard, pick up the bottle, look at it has vinegar, which is acetic acid, and water, which is a carboxylic acid, and think about all the condiments you put on hot dogs or hamburgers. Most of them are acidic because of acetic acid. All right. Guess what time it is? No, it's not time to leave. It's time for new functional groups. New functional group time. And those new functional groups are carboxylic acid derivatives. Ooh, fancy new word, derivatives. What derivatives mean is something derived from or made from. So these new functional groups are made from carboxylic acids. And they're compounds in which the hydroxyl group of a carboxylic acid is replaced with other stuff. Well, that sounds scientific, other stuff, but it's true. So let's go ahead, and I'll never ask you what is a carboxylic acid derivative on the test. One derivative is called an ester. And an ester, well, I better warn you, coming up, I'm going to talk about something that smells really good. And I'll tell you a personal story of mine which involves Marshall Field and alcohol bases. All right. Ester is where you replace the hydroxyl group with oxygen and R prime. And that's called an ester. And it turns out, most of you don't realize it, but you use esters all the time in your daily life. And the other group, which unfortunately I don't really have time to talk about this semester, are called acyl or acid halides. And we've talked about one in Friedel-Crafts acylation. That's an acid halide or an acyl halide, where X is a halogen, chlorine, bromine, or iodine. I've never seen one with fluorine. And so these are two derivatives. There are other ones, but these are two derivatives of carboxylic acids. Again, derivative, something made from a carboxylic acid, and esters and acid halides. But in this class, I'm going to spend time talking about esters. What is an ester? An ester is a carboxylic acid in which you replace the hydroxyl group with an oxygen and R prime, other carbons. And this is called an ester. Now, first thing is, how do you name esters with the IUPAC rules? Remember, IUPAC is the organization, which I'll never ask in a test, but I like to say, International Union of Pure Applied Chemistry, that's responsible for all the rules for naming chemicals. And most of their chemical rules are for organic compounds. So let's put an ester on the board. And the first question is, if you're playing that fun game, circle and name the functional group, what functional group is in this molecule? Well, what's different? Ooh, two oxygens. Notice this oxygen, double bond to carbon. This oxygen is on the same carbon. On this carbon, the carbonyl carbon, we have carbons. And on this oxygen, we have carbons. I'll call that R and R prime. Therefore, this is an ester. Question is, how do you name an ester? Well, the first thing you do is you look at R prime. And you look at R prime and you pretend it's an alkyl group. Anybody see an alkyl group that's familiar? Ethyl. Therefore, at the beginning of the name, you put the name of R prime as an alkyl group. Now, the next part, there are two ways of doing it. I'm going to first do the IUPAC way. Then, a number of semesters ago, I had a very clever student, and that student said, I have a better way, and that works about 95% of the time, and I'll teach you that too. And as you can see from my personality, who I am, I don't take credit for somebody else's good work. And it really does help students. All right, let's look at the first part. All right, one, we've already done. Name R prime as an alkyl group and put that in the front. The IUPAC way is assume R prime is a hydrogen. Name the carboxylic acid. And another way of stating that, and you'll learn later this week, in fact, some of you will do it today, and I'll go through the reaction, so I won't get to it. No, I might get to it today. That would be used to make that. So if this were an H, I have 1, 2, 3 carbons, that's propane. Drop the E at OIC and the word acid. But now, what you'll do for the ester is drop the IC and the word acid and add ATE. And therefore, this becomes ethyl propanoid. Say that 5 times quickly. And that's how you do it. Now, there's a to be, or not to be, that's the question. I can't resist saying that. Anyways, for those who know Shakespeare, but never mind. All right, the one idea the student came up with is name the chain with the carbonyl carbon as an alkane. 1, 2, 3. Propane. I'm going to move this up here because this way you people in the back can see it. And then continuation of to be or not to be. Drop the E and add OATE. And if I look at this again, the R prime still in the front is ethyl. Next, I have 1, 2, 3 propane. Drop the E, and now you add, instead of ATE, OATE. You get the same name. There's a couple of places where this fails, and I'll show you. But for the most part, the 2B method is probably easier for you to remember. Let me do one more, and then I will share. And that is, what's the IUPAC name for the following? And you look at what functional group am I dealing with? What's different? 2 oxygens. 1 is double bond to carbon. To that same carbon, I have another oxygen. I have carbons here, R prime, carbons here, R. I have an ester. How do you name an ester? You find the R prime, and you name it in the front as an alkyl group. 3 carbons, center carbon, that's an isopropyl group. Then, what's probably easier, use the 2B method. Try not to say what I want to say, but I'll stop. 1, 2, 3, 4, butane. Drop the E, add OATE, and that's isopropyl butanoate. Say that 5 times quickly. And that's how you do esters. Why don't you try this one? What would be the IUPAC name of the following? On test number 3, will this be like test number 2? Approximately the same number of points, approximately real world general knowledge questions. There'll be about approximately the same amount of nomenclature questions. perfect. And then there'll be about the same amount of points as reactions, which in the last test was, I believe, 10, 35, and 60. And I'll post that before the test. And it'll probably be about 9 pages. And if you know your stuff, like the last test, which should be out of here, we start at 10, which we do, you'll be out of here by 10:40 at the latest. If you notice my test, I allow you to have enough time to finish it if you practice. All right, let's take a look at this. If we look at this compound, the question is, what's the IUPAC name? First thing you have to do is identify what functional group are you dealing with, what's different. Carbon with oxygen, oxygen here. Carbonyl, oxygen, carbons on the oxygen, I'll call R prime. Carbons on the carbonyl carbon. Ester, how do you name an ester? Carbonyl R prime, how do you name that as an alkyl group? 3 carbons to the N carbon, and propyl. Now, one of the things I should caution you about, when I write on the board, I just happen to haphazardly do capital and small case most of the letters. And when you're typing or keyboarding, I don't think anybody types anymore, you should all have lowercase, the letters of the name. But it's very important that this N is always lowercase, because we'll learn later on, capital N means something totally different in IUPAC name. All right, let's continue on. What's the longest chain with the carbonyl carbon? 1, 2, 3, 4, 5, 6. Hexane. Drop the E and OATE. If you had said hexanoic acid, drop the IC in acid, add ATE, you get the same name. Now, where 2B fails is for the following ester. And you have to know the IUPAC name. And if we look at this molecule, wow, there's a benzene ring in it. Well, what's the key functional group? Carbonyl with an oxygen. On the oxygen, I have carbons, R prime, actually 1, but it's R prime. On the carbon, I have the benzene ring, but that's R. So how do you do this? This is an ester. Name the R prime as an alkyl group. When carbon, oh, it's your old friend, the methyl group. And now you have to use 2A. Pretend this is a carboxylic acid, which would be this, which is benzoic acid. For the second part, drop the acid, drop the IC. Add ATE for 2A, and that's how you get the name methyl benzoate. Because you can't say what's the longest chain here, because it's not a chain, it's a ring. Now, another functional group which I've talked about, but I haven't taught you until now, the name of how to use it, derive the IUPAC name, is this. This is where you have carbonyl, oxygen minus, and a cation. This could also be a +2, and this is called a carboxylate anion. And how do you name them? Let's put one on the board. First of all, this is a carboxylate anion. How do you know? Carbonyl, oxygen, other oxygen with a negative charge, cation, and R group. Carboxylate anion. Now, for a carboxylate anion, first thing you do is you look at the cation, what has a plus charge. You look what element does that come from. And Na, I hope you all know, is sodium, and that goes in the front. Next, you name the rest of it using the same rules you do for esters. So how many carbons in the longest chain? 1, 2, 3, 4. That's butane. If we use 2B, drop the E, add OATE. And this would be sodium butanoate. Now, how do you tell the difference between an ester and a carboxylate anion? Well, in the front of the name, if there's a metal or the name of a element you know is a carboxylate anion. If it's the name of an alkyl group, you know it's a ester. Now, one of the things that can happen very quickly with both carboxylate anions and esters is if you have alkyl groups on the chain. And the carbonyl carbon is 1. You don't put a number where it is because that's always. But if I had a methyl group here, this would be sodium 2-methyl butanoate. And it can be very challenging very quick. It's time for a little gift from Dr. White. On my test, and I think the ACS does the same thing if I remember correctly, I will never put an alkyl group on the chain of an ester. But every little bit helps. So, there's 2 types of IUPAC nomenclature skills you should have for organic chemistry, which is another way of saying there are 2 types of problem questions I can put for nomenclature on tests. One is, here's the structure, give the IUPAC name. The other is, here's the name, give the structure. Now, before I do that, there's one common name I would like you to learn. Nope, I don't have a slide for it. And the one common name for esters is this molecule. And this molecule, the IUPAC name, which nobody ever uses, are prime ethyl. How many carbons? 2, ethane. Drop the E, add OATE. Common name, which everybody uses. R prime, you do the same. Ethyl. But for the carboxylic acid under 2A, instead of using the IUPAC name for this carboxylic acid, that would be used to make this ester, you use the common name, which is acetic acid, and you drop the IC in the word acid, and put ATE, and this is called ethyl acetate, which everybody calls it. And a lot of you might have ethyl acetate in your house. You say, no, I don't have ethyl acetate in my house. Yes, you do. Where do you find it? It's one of the two molecules that's used for nail polish remover. Ethyl acetate is used for nail polish remover. If you went back about 5 years ago and went to somewhere like Target or Walmart, which I do things like this, and yes, I am an organic chemist, and you walk to a section where they sell nail polish and nail polish remover, you would see about 90% of the bottles are ethyl acetate nail polish remover. Look at the label, it says ethyl acetate. Put a little perfume in there. And the other 10% is acetone, which is nail polish remover. But in the last couple of years, I think most of you are aware of, or many of you are, the new super durable nail polish. You can see I use it. But anyways, ethyl acetate has a hard time taking it off, I've been told, and acetone works better, so I think acetone is making a comeback. Why has ethyl acetate always been in the majority, or at least a number of years? Because it doesn't sting if you have any cuts or anything on your fingers the way acetone would. The other nomenclature skill, now that you have the common name, because on the test you see me put down, draw the structure for the molecules with the following common or IUPAC name, and how do you decode this name to draw the structure? You start at the right, move this way. OATE, either an ester or a carboxylate anion. Alpha group in the front, ester. If this were an E, octane, 8 carbons. At one end, you have carbonyl with an oxygen. On that oxygen, at the very front is R prime, which in this case is methyl. And there you have methyl oxygenate. I should tell you, and I'll do it in the next slide if I get to it, which I should. Dr. White loves esters, and Mother Nature really, really, really loves esters. All right, let me have you try one. Draw the structure for the following molecule, T-butyl propanolate. And if anybody came in late, see me right after class if you didn't pick up your test yesterday. Let's do this one, then I'll have you do that one. Let's take a look at this. How do we decode this? You look at the name, start at the right. OATE tells you either ester or carboxylate anion. Alpha group in the front says ester. Therefore, propane, if this were an E, 3 carbons. At one end, I have my carbonyl, my oxygen. Next, I look here, T-butyl, oh, it's my favorite, is the R prime. Remember ester? that? R prime is T-butyl. And we're done. Why don't you try this one? Potassium benzoate. What would be the structure of potassium benzoate? Let's say when you're done, look up and give me the high sign, but I don't think anybody here has ever seen Our Gang. TV show, actually was from there before even TV, but I see it on TV. Look on YouTube. Just about everything's on YouTube, I think, except my college graduation. All right, let's do this. How do you know what to draw here? You start at the right. OAT, ester or carboxyl. Ooh, element in the name. That means it's a carboxylate anion. What's M plus? Potassium, symbol for potassium is K. And therefore, if we, benzoate, where does this come from? Benzoic acid. And benzoic acid, because now you have to use 2A, is this, but it's a carboxylate anion, which is this. I have a negative charge, and what's my cation? Potassium plus. And that's how you do it. Now, one of the questions you should always be asking yourself in my classes, why am I learning this stuff? And besides the obvious, you want to get a good grade in someone so you can take this class, get into a program in your school. Why learn organic chemistry? Well, it turns out esters are in nature, big time. Mother Nature loves esters. Coming with spring, or if you happen to go into a florist shop or a part of Jewel where they sell flowers, actually a florist shop is better. Or somebody is nice enough to give you some roses, what do? You smell the flowers. And I don't know about you, but I love springtime because you go out for a walk and smell all the amazing scents from the flowers. Everything you're smelling is an ester. Flowers give off esters, and that's what you smell. And also, many of the fruits and vegetables, when you have a banana, if you smell and taste the banana, what you're smelling and tasting is an ester. Now, how does that affect my nose and tongue to tell me, that's a banana? Don't know. That's not my area of expertise. The molecule that's responsible for banana is called pentyl acetate. That's the common name. And if you look at a rose, and don't write this down, I'll never ask this, but a rose, various roses, volatile esters, that means you can smell them, are coming. These are some of the ones that have been identified, very complex esters Mother Nature makes. And you don't know about this, but now you will. Some of the most sophisticated organic chemistry is perfumes. Perfumes are mainly esters. And time to tell a true story. When I was in high school, I had a bad habit. That was, I could get my mother real upset at me real quick. And I did that once in a while, and I mean, she was ballistic at me. And the only way I would get out of the doghouse, I don't know if you're familiar with that term, have her not be mad, really mad at me, was I'd go over to Marshall Field near our house and buy her favorite perfume, which was Chanel No. 5, which is not cheap. And after a while, the women at the perfume counter at that Marshall Field got to know me, and if they saw me, oh, did you get your mother mad at you again? And the answer was always yes. And they'd ask how mad, and I said, like this size bottle, the more mad she wasn't need a bigger bottle. And that stuff was not cheap, especially when you're in high school. So I finally learned not to get her mad at me. I guess that's part of being a teenager. All right, another thing, animals use esters. They're called sex pheromones. And sex pheromones are used mainly, but not totally, and here I'm way beyond my level of expertise, by the female of the species when in heat to attract the male for reproduction. And various animals use esters. Now, sometimes scientists use esters to trap animals like insects too, like moth, gypsy moths. They made the sex pheromone for the gypsy moth, and they put it in traps so they could trap all the males and cut down on the population. And they do that. Now, for many, many eons, the question is there a sex pheromone for humans? And so far, nobody's found one. If you do, you're going to be wealthy beyond your dreams, wildest dreams. A couple of years ago, there was the news. You hear every couple of years, someone has discovered this is a sex pheromone that attracts so-and-so sex. And I don't know if you buy into it, I didn't. Some researchers claim male sweat attracted females, but of the opposite sex. I don't know about that. But they do use that logic in commercials. How many of you are familiar with the product, and I don't get any kickbacks from them, called Axe? It's cologne for men. Cologne is a fancy word for men, meaning perfume. But it's called cologne, because men don't put on perfume. But anyways, they have the ads and so on TV. Some guy puts on some Axe and all of a sudden goes out the front door and all these beautiful women attack him. And that's a play on, is this a sex pheromone? And they're esters too. And about 10, 20 years ago, same commercial, different name product called Canoe. And they say, do you canoe? And the guy would put on some, walk out the door and get jumped by a lot of beautiful women. So Madison Avenue advertising tries to do that. I don't think so. If I'm giving you a headache, you can take some aspirin. You don't have to write this down. Aspirin, this is the chemical structure. It's an ester, it's an aromatic compound, it's a carboxylic acid. It was discovered by a chemist for a German company, A.G. Bayer, which is why they call it Bayer aspirin. They were the ones who originally discovered it. And the story goes, his father had arthritis. When he would take this, it would help him with the pain from the arthritis. It's about 1900, except his father would get an upset stomach. And if you notice, you've got a carboxylic acid. Putting acid into a stomach that's sensitive is not good. So the chemist neutralized that, reacted with some base, put a carboxylate anion instead of carboxylic acid, still relieved the pain, and they called that bufferin. And I don't know if you remember the product, which isn't that popular as it used to be, called bufferin. That was aspirin where you neutralize the carboxylic acid. All right, real quick, because you're going to see it Tuesday and Thursday, I'm just going to show you a slide. How do you make an ester? Carboxylic acid plus an alcohol in the presence of acid, sulfuric acid. Usually you make an ester. How am I doing on time-wise? Oh, I got time. Oh, 30 seconds. This was discovered by the great German chemist Emil Fischer. This alone would be a lifetime achievement to discover this reaction, but he's well known for something else, which we'll get into. He elucidated, figured out, it's a fancy word, figured out the structures of all the small sugars. And that won the Nobel Prize. This should have also, but it also killed him. And I'll talk about that when we get to carbohydrates. And that's a pleasant note. I still have 50 seconds, but I'll let you out now. For those of you who have lab today, please be on time. Make sure you